Welcome back. This is lecture number 37. In this lecture, we are going to talk about accurate small signal modeling under current mode control and verification using MATLAB. So, in one of the previous lecture, we started with the first order model, that means the impedance analysis with closed current loop, right. So, we took current mode control and use a very basic first order model, right, and we derive the equivalent circuit, and then we obtain the equivalent circuit and then derive the various transfer function. So, today in this lecture we want to first recap that what we learned in the first order approximate model, and then we want to come up with more accurate model. What are the other modeling technique, where are the sources of inaccuracy and how can we improve it, and then finally we want to show some MATLAB case study with some model matching, okay, under current mode control. So, recap, we want to approximate equivalent circuit model in canonical form. In a generic DC-DC converter, this model we have already obtained, and this model is well known, and it is this model, all these parameters are available in Fundamental of Power Electronics book. And if you go back to the previous diagram, so from here we can find out audio susceptibility, output impedance, control to output transfer function, various transfer function under current mode control, but these are all under current mode control. Okay. Now, you will find this G of 2 is 0, and if you go back, this G of 2 is linked with input voltage. That means, we will see for a buck converter, this approximate model, if you try to derive audio susceptibility GVG, right, which is V0 by V in, it will be simply 0 in this case, because G2 equal to 0, which means it indicates there is no effect in the output voltage for a change in supply voltage, but it will not be the case for a boost converter. There will be a first order effect, but here we are only talking about buck converter model matching, because we have a separate lecture for boost converter model matching and current mode control design. So, that means audio susceptibility 0 means this is something which is very much approximation, but we need to figure out, otherwise this model first order is quite nice, very simple, and we want to check whether this model how far it is valid. So, output impedance of the practical buck converter that we derived, so it was R ESR, because this is under current mode control when we converted this inductor current into a control current source, right. We converted into a control current source, because we have assumed that average inductor current can be replaced by average peak current, and we are directly controlling the peak current, by which the inductor becomes a control current source. So, this is the assumption, since the inductor becomes a control current source, the inductor current dynamics is not coming into picture. And for the output impedance, we ignore the change in control perturbation in the control signal. That means, we are using a fixed current difference, but the inner loop is closed, remember inner loop is closed. So, this is our expression with a load resistance for a buck converter, ESR 0 and pole. Now, if you see this output impedance under duty ratio control, what we found under duty ratio control? For duty ratio control, that means what was our output impedance when we are talking about minus V0 by I0 hat with D perturbation V in perturbation equal to 0. We found that in practical there is a R equivalent by alpha multiplied by, there are two 0, the polynomial is 1 by S q omega 0 plus S square by omega 0 square. We found, okay, so let me write, we need some space, so I will write it here. So, that means output impedance we found Re by alpha into 1 plus S by Q omega 0 plus A square by omega 0 square. And 2 zeros we got 1 plus S by ESR and 1 by S by omega L. And what was omega L? It was Re equivalent by L. And R equivalent we know it is RL plus RDS on. So, in duty ratio control, the common thing you will find this is coming into picture. That means, for an ideal buck converter, the output impedance, this term will not be there, okay, and this term will not be there. So, output impedance will have only RLC circuit, that means there is no parasitic component. So, ideal case, for ideal case, if you write, even if you apply limit S, that this coefficient Re tends to 0 and other term. So, ideal case output impedance can be written as that delta S remains same, it will be simply SL. So, here only omega 0 will be, in this case omega 0 will be 1 by square root of LC and Q is simply R by L. So, these things are known. But when you close the current loop, then the output impedance is different, drastically different. Your ESR 0 is there, but pole is become a single pole like a first order, and pole is a function of 1 by RC because this branch look like RC circuit. But what is the problem? The output impedance, you see, its DC value is a load resistance dependent. That means, the output impedance with closed current loop under DC behave like a resistance. So, that means, if there is any load step change, the output voltage will immediately change by the load step multiplied by the R and the negative value, right. So, which is not desirable. So, that is why the current mode control suffer for poor load regulation because of high output impedance for closed current loop. Okay. Now, if you take a practical buck converter control to output transfer function, so it is same as the output impedance, only earlier it was an external sink load, now that is replaced by a source side control current source, that is it. So, that means, here it will be V0 by IC by taking other thing constant, and here it is minus V0 by I0. So, one way the load current is sink current and here the control current is a source current. So, same branch. As I said that in this case, if you get the DC gain, that S equal to 0, it is totally load dependent. That means, even if you want to design a closed loop control, this control to output transfer function is a part of the loop transfer function, and the loop transfer function gain, DC gain becomes load resistance dependent. And if there is any change in load resistance and which is about to happen, then you have a severe problem with our DC gain problem. Okay. But this approximate model is very useful in terms of robust compensation because there is no double pole anymore. So, they by virtue of closed inner loop, one pole become much faster, and which is the inductor pole which go very far in the left hand side because inductor become a control current source. So, we are almost taking that inductor behave immediately. Now, we want to verify this small signal model current mode control with actual switch simulation, how far it works under closed loop. So, first we want to do reference step transient, then closed loop output impedance, step left transient, and we want to link audio susceptibility. These three we want to do, right. So, we already have MATLAB code. So, let us go back. So, we are talking about this is a first order model, and if you see the first order model, this is a parameter file that we call load resistance, then this is our ESR 0 and this is a single pole. That means, if you try to map correlate, so this is our single pole omega p and I take omega z to be ESR 0. okay, ESR 0, okay, ESR 0. Then what is the control to output transfer function? It is R times 1 plus S by W ESR, and denominator is 1 plus, because in transfer function we write the S polynomial coefficient first and then constant term, right. So, this is my control to output transfer function. So, it is very simple. The output impedance open loop is same as the control to output transfer function, but I am writing again. Then I have set some arbitrary value of PI controller, because it is a first order system, and we will see in the next lecture a PI controller or a type 2 compensator should be sufficient. And I have taken a PI controller KP80 and it is like a 300,000 is my Ki, okay. So, Kp Ki is just a PI controller. Then the closed loop gain, which is our loop gain, is the product of the control to output transfer function multiplied by your controller. Then what is the closed loop output impedance? It is nothing but open loop output impedance divided by 1 plus loop transfer function. The closed loop transfer function is loop transfer function divided by 1 plus loop transfer function. And here we have all the Bode plot. So, once we loop transfer function, and we can find out the gain margin, phase margin, bandwidth and crossover frequency and all. So, initially we want to carry out a reference voltage transient, because what is our initial target? Reference voltage transient. This will give us the bandwidth concept, okay. So, then we want to match the model, okay. Okay, just a minute. So, for we are using a very small ramp compensation, very small, it is almost negligible, okay. And if you go back to the current mode controller block, I am using a very small compensating ramp Vm, which I am setting 0.001, that means it is 1 millivolt, which is negligible, that means as if we are not using at all. Then if I go back, so I got phase margin 94 degree, which is like very much overdamped system, but gain crossover frequency to be very high, 63.86, whereas 500 kilohertz is my switching frequency. So, it is roughly 1/8 of the switching frequency. That means, we are going even further, we are increasing the bandwidth or crossover frequency compared to voltage mode control. Now, we want to match this response and see what happens. Okay. So, we want to compare. You see, the red one is the response obtained from the first order model, and the green one, a blue one, is the actual switch simulation. Okay. So, this is like a first order system, and since we are using a PI controller, so this is coming from, though they are not matching exactly, but they are reasonably matching, right. At least if you see the initial phase, yeah, that means there is a model matching problem. So, here we should reduce the controller gain in order to reduce the bandwidth, because we are going for 1/8 of the switching frequency, where there could be a model matching problem. Another aspect we want to see, the model matching problem can be due to the first order model. So, we do not know, okay. But let us do one thing, if we reduce the controller gain, that means instead of using very high controller gain, so if we reduce to 60 and if we reduce to this, and let us again try. Now, it will show all the bandwidth, okay. Now, this time the model is matching to some extent, except there is a shift in the DC value. That means, you see there is a DC shift, the red color is shifted up slightly, okay. So, this DC shift is coming because of what? Because if you go to the current waveform, you see we have taken that peak current, we are controlling peak current, but we have assumed the control current is equal to peak current, right. That means, if you go back to our initial assumption, what was our assumption? Our actual control is like this, peak current, this is my control current, and we are taking this is my average inductor current. So, we assume that this control current is approximately equal to IL, but unfortunately at light load condition, particularly if you see the waveform here, your peak current is roughly around 2 ampere, whereas the average current is just above 0, very low. So, this can cause some decisive problem. So, whether can we solve this problem by increasing the load current or decreasing load resistance? Suppose if we use 0.05, then now we are operating like a almost 20 ampere current. Okay, now we want to see what happened. So, now gain crossover frequency is reduced, it is less than 1/10 because we are using a lower controller gains, smaller controller gain, but we want to check whether the matching is still, mismatch is still there or not. Okay. So, actually integral has we need to increase the integral gain because it has not reached steady state. So, we need to increase the integral gain. I will tell you why, because if you go back to our past, so this omega p, what is omega p? Omega p is our 1 by RC, right. That means, if you reduce this pole become faster, right, but at lower the DC gain is also falling, right, because at lower resistance value we are reducing the resistance value, the DC gain is drastically falling. As a result, it will take longer time, that means the lower DC gain, it will take longer time to reach to steady state. So, in order to anticipate, you have to increase the earlier we are using in one case in 10 ohm and the other case we are using 0.05 ohm. So, that means we have reduced significantly this R value. As a result, your DC gain is also falling, it is also getting reduced, and that is why it becomes sluggish, it takes lot of time to reach to steady state. Okay. So, then how to solve this problem? We can simply increase we have increased the integral gain, and let us see, in order to now it is slightly faster. Yeah. So, it looks like now they are matching closely. That means, now you can see the DC matching problem, they are closely matching, because earlier the mismatch, one of the problem with the mismatch was our initial assumption. That means, we have taken the control current is equal to the average current, which makes sense when the load current is high, because if you go back, if you see here, if you see here, your peak current is 24 ampere and average current is 22. So, if you take the ratio, that peak by average by peak, that is almost close to 1, it is not very low. But earlier we took, the average was close to 0 and peak was 2. So, there is a significant deviation, and that was causing the problem in this case. Okay. So, that means, this actually tells us that this model limitation is one of the limitation is this assumption itself, and this works fine when you are talking about high load condition. Okay. Next, we want to verify the step response for load step transient. Okay. Go back to our simulation result, and we want to verify for load step transient. So, if you go to load step transient, now what we have to do, we need to set, let us say we are making 20 ampere and we are putting the resistance initially 1 ohm, we want to change from 1 ohm to 20 ampere, 1 ampere to 20 ampere. Okay. So, here this part I have discussed earlier, I have to set closed loop output impedance and I have to multiply with, now we are applying load step transient, okay, again 0.01, and we want to check what happened with our simulation. So, there is showing load step transient, and you can see this initial jump is closely due to the ESR jump, because you see there is a ESR jump. So, there it is closely capturing the ESR jump, okay, and that we saw in our earlier small signal model, and you can see the response is matching reasonably accurately, I mean quite nice. You can see they are coming close. So, that means this first order model works fine as long as, and here the load current is undergoing transient from this to this, okay, even with huge duty ratio variation, because there is a large variation particularly this particular cycle, but still our model is working reasonably well. So, it is well, we can design. The next part, supply transient. So, since audio susceptibility is 0, so there is no question, but this can cause some problem. So, now even with our for our case, if we do supply transient, so we want to see, we are assuming this model tells that there will be no change in the output voltage if you make a change in the supply voltage. So, we want to make now supply transient. So, load transient we have removed. Let us say we are making minus 5 volt supply transient. So, okay, so we do not want to plot, because supply since is 0. So, this plot we want to avoid. Okay, so 0.001, and the next is that we want to show. So, we made a supply transient. So, our model says there is no effect, but actually there is a slight effect, although it is negligible. So, that means it is reasonable. The current mode control has a very excellent audio susceptibility, or you can say the line regulation. So, there is no problem. So, it immediately responds. That means almost no change, because it happens in the order of even less than 1 millivolt, I mean few millivolt, less than like 1 or 2 millivolt. Okay. So, that means we have checked, but limitation of the first order model we have identified. So, there can be inaccuracy due to that whenever the load current is light, then the mismatch will come, because average is not same as the peak, that is one. Second thing, here we have not considered the modulator gain, because even though if you use ramp very low value, the model will significantly deviate if the ramp slope increases, if you increase the ramp slope, because there is no provision in our model to accommodate ramp, and that is one of the problem, because ramp is needed when the duty ratio is higher than, or even it may be lower than 50% also, like around 0.4, 0.45. If you increase, if you use a high gain, you may get first like a subharmonic instability. Okay. So, that will be a problem when you use a ramp compensation, that can cause some mismatch in this error. So, now we want to go for a better model. So, first we want to understand peak current mode control. Then what we are going to do? We want to improve the model accuracy. Now, we want to, that actually lies with the derivation of the modulator gain. Okay. So, if you the first approach, if you take the first approach, it is derived by the Middlebrook approach, where we are taking a ramp compensation here. So, this is our ramp, this is our due to ramp, because we are, what we are doing here, we have a reference current, this is our IC here, and we are subtracting ramp, because we can add ramp with the current, or you can subtract the ramp from the control voltage, control current. So, that is exactly what we are doing, and this is my ramp, basically minus of the ramp, and then we want to derive the average current expression in terms of this current. That we Earlier we took IL average equal to IC average, but now we want to introduce the duty ratio information. So, find the average current. Average current here in this case is nothing but this point minus half of the ripple, right. So, this is minus half of the ripple, So, it is, what is this value? This value is given here. So, average of this minus delta L by 2. And what is delta L by 2? It is, what is delta IL? Delta IL we have learned earlier, it is M1 dt, right. So, delta L by 2 is this. Then step 2, you can now consider the steady state quantity and part of quantity, and then obtain the part of equation. So, from there if you obtain the part of equation, you will find out that the part of equation, the duty ratio perturbation can be written in terms of modulator gain, control current, inductor current and this. So, earlier these two was taken equal. So, that is why that there is no duty ratio expression, but now we have not taken equal, and this is a modulator gain, right. So, this is something similar to what we did earlier, that we are trying to find out the duty ratio expression here in terms of control current and also inductor current, and M1 will also carry voltage input output voltage information. Method 2, another way. Now, average inductor current, earlier we took that only for this cycle, that means we have only considered this cycle, the average inductor current was equal to this value minus half of the ripple, but this may not capture the full picture. So, we want to take the average inductor current over the entire cycle. That means, here the average inductor current is nothing but, if we take the average inductor current in part 1, this is my part 1 and this is my part 2. So, here the average inductor current is averaging over dt time, and here I am averaging over 1 minus dt time or d dash time. Here I am taking 1 minus d equal to d dash. So, then if we average the overall average d into this 1 minus d into this is exactly is done here. Then if you apply substitute that equation, what is IL average during dt time? So, IL average during dt time is nothing but that, if you go back from the waveform, in this interval it is nothing but IL average dt time is nothing but this value, that means IC minus MC dt minus your delta IL by 2, which is nothing but M1 dt by 2. Next, what is IL d dash t? So, this point is common for this, right. So, it will be IC minus MC dt, it is there, but now minus half of the ripple we will take in terms of this slope, because we are talking about this particular sector, right. So, ripple can be expressed in terms of falling slope also. It is M2 1 minus d by 2 divided by 2, and if you multiply 1 minus d, this will be square. Okay. So, this is exactly what we are doing here. Here IL dt, and then you substitute, you will get this term. Now, you part up. If you part up, then you can IL perturbation, and since d 1 minus d both are, this term is common. So, they will add up and become 1. So, IC perturbation, and since this is constant, so in fact we should write MC directly here, we are not perturbing the slope. Then for this term, once we will consider perturbation in the duty ratio, and the other time we will consider perturbation in the slope. Okay. So, if you consider perturbation in the duty ratio, so M1 T d square by 2, then we simply partially differentiate with respect to this, and that is computed as d equal to capital D. Then what we will get? You will get 2 times m1 t. This is computed at m1 equal to capital M1. So, this will be capital M1 and this into d divided by 2. So, it is simply m1 dt. So, this is exactly here. Similarly, you can take the partial derivative of this with respect to duty ratio, then you will get this term, okay, and there will be a negative sign, and negative become positive. This term will become positive. And similarly, you can take perturbation in the time here. So, then this term will be fixed. So, this is simple. By that, we can obtain the duty ratio perturbation, because we have already obtained this. Now, we have to take duty ratio perturbation on the left side and all other term to the right side. Then, whatever will be divided Fm, that modulator will be MCT. That means, in this case, the modulator gain is purely MC dependent, compensating ramp, and that is why in the earlier simulation we took a very small MC. If you do not take MC equal to 0, then this Fm becomes infinite, right. That means, without ramp compensation this will become infinity, but if you take a very slope Fm, then it will, and I will show you for a higher Fm or smaller MC, this model what we are going to derive will almost resemble the model of the first order model. Okay, since at steady state M1D, that the coming from the, that means steady state ripple, this is coming from the steady state ripple criteria. So, in a buck converter you can write M1, M2 perturbation. So, it will be, so that means you can find out the term associated with V in perturb, V0 perturb. Then you can tabulate the modulator gain in method 1, the middle book method is this, then dt by 12, 12 minus dt by 12, then you can write 1 by MC d square t by 12. So, all these things we can write. But interestingly, if you take in method 1, for example, if you take 2 microsecond is our time period, 0.5 microhenry is our inductor, d equal to 1 by 12. So, dt by 12 will be 1/6. That means, if you take compared to the actual inductor current scaling dt by 2, so this has negligible effect. So, it has a negligible contribution. Okay. So, we may drop this negligible contribution for sake of simplicity, but if you want you can include it, ignore. So, this term is ignored, it has very negligible contribution, but we can include it if you want, then there will be an additional loop of the voltage. So, now this is our circuit that we have discussed. That means, since we have ignored the perturbation due to the output voltage, otherwise there would have been another loop which should come K2 and there will be V0 and this will be minus. So, this term we have ignored, because we have initially assumed that dt by 12, that term is very small. Okay. So, now this is the loop structure. This is our original small signal AC equivalent circuit of the buck converter, which we have derived for voltage mode as well as the open loop. Now, we are putting this current mode control loop, that means there is a current loop, you see the feedback current loop, and this control current is generally generated from the outer loop. So, that means it is a 2 loop control. This is the inner loop, this is a current loop, okay, which is the inner loop, and there is an outer loop will be there if you close the outer loop. Okay. Now, this Fm we have derived. So, this can be obtained. What is Z1? We have taken this to be Z1 and Z0 is the output impedance of the buck converter, which was when we close the loop, close the current loop for approximate model, this was our output impedance. But if you sum these two, that means if you take the entire branch, in this circuit it is nothing but the input impedance. Okay. So, Zin, so effect due to output voltage perturbation is neglected. Now, this is the overall small signal block diagram, and you can simplify this IL from this block diagram. So, I am not going to talk about this. I want to find out what is my current loop transfer function. So, that can be, if you take the whole product, then it will be V in Fm by Z in. Okay. So, this is my loop transfer function. Now, adding a separate current loop gain. Suppose you put a Currentsense amplifier which has a gain, which may not be unity because you want to scale it. This can also include, suppose you have used a sense resistance. Suppose you have used a sense resistance Rs in with actual inductor current. But this sense resistance will also have Currentsense amplifier, right. So, there is a Currentsense amplifier which will also have some gain, the gain of the Currentsense amplifier, right. So, whatever we are getting, the sense voltage we have discussed, it is nothing but some current loop gain multiplied by your actual inductor current. Okay. So, this sometime we want to reduce the gain, because if you want to increase the gain, there is a gain bandwidth product of the Currentsense amplifier, because the high side Currentsense amplifier there are some dedicated commercial IC which has a limitation in the bandwidth, and if you want, and also a gain, that means there is a gain bandwidth limit. But we can incorporate this Kc also. If we incorporate, then our M1 slope, because in actual I am talking about the actual current which is compared. Now this is our sense voltage which is equivalent to current, and this slope will be M1 into Kc, because it includes the Currentsense amplifier and everything. That means it is not exactly inductor current, it is a scale version of the inductor current. And under this, okay, it is shown here. So, under this you can draw the waveform. This is my sense voltage, okay, as if it is like a filtered current, or you can say sense voltage. Then modulator gain will also scaled up, because if at all it has, method 1 will scale up wherever the actual current slope will be there, but for ramp it does not matter, because ramp is independent of this. So, accurate small signal block diagram can be updated with the Currentsense amplifier gain, and we can modulator gain. So, this is a current loop gain, updated current loop gain. Now, control to output transfer function, if we take this diagram, okay. So, what is the transfer function between IL and IC? Suppose our V in per term is equal to 0. So, I can discard this part. Then what will be my transfer function, and suppose we take Kc equal to 1, suppose we take Kc equal to 1, then our Ti will be V in Fm by Z in. Okay. So, under this case, what is the transfer function between IL and IC? Okay. So, these two transfer functions. So, this will be simply, this is in the forward path, right, this is my forward path, and since Kc equal to 1, so forward path transfer function is same as the loop transfer function, current loop transfer function. So, it is simply Ti by 1 plus Ti. Now, if Ti is very high, if Ti is very high 1, then this will be approximately equal to 1, and we have started with the first order model that IL perturbation is replaced by IC perturbation, and those are correct as long as the current loop gain is very high. Okay. So, if the current loop, this is output impedance expression. So, that means closed loop block diagram, if we consider a current, that means current sensor. Okay. So, closed current loop. Now, if the current loop gain is very high, then the output impedance with this model will be same as the the model of the earlier model, and here I am taking GCC equal to 1. Similarly, the GVC, if the current loop gain is very high, it is the same as these two, right. Now, we want to verify, that means let us go back to the MATLAB and we want to verify. So, now we want to verify these two model. Okay. So, one case we are using 001, okay, and this is a loop transfer function of using the first order model. Now, same ramp we are using 0.001 and this is a loop transfer function and we want to compare. Okay, so let us first set the hertz in frequency and limit we set 5 e minus is 5. Okay, that means this is our switching frequency, and you say the loop transfer function, what are the stability margin? So, it is phase margin is 93.7 and frequency is 47.8. It is like almost 1/10 switching frequency, and they are matching quite nicely because both they are almost overlapping. If you go further down, they are almost overlapping. Okay, so they are overlapping and they are almost close. So, it is expected that their transient performance will be also, it should match. So, we will also run the transient performance and check. Yeah, so this is actually okay. Let us also use uncomment because we want to plot the model one as well. Okay, so if we run it again, it will show that the model is working properly. So, this mismatch problem is solved because this is a more accurate model. Okay. And on top of this we can also plot the response obtained from here. That means they will be almost identical because that we have seen earlier. The only offset problem is solved with the more accurate model, otherwise they are matching quite nicely. But now what happens if we increase the modulator gain, that means slope is increasing. Now we are running the same condition, let us say 0.1. Now the slope of the ramp compensator is that means not slope, I think the voltage, earlier it was 0.001, 1 millivolt, now we are using 100 millivolt, which is still low, but we want to see whether the model matches or not. 0.1. You see the model start deviating. Okay. So, if I take the limit, because this is our switching frequency. So, because of current loop gain is now start falling and they are not exactly identical. Particularly you will see the model which is the first the improved model provide more phase, almost there is around 20 to 30 degree, around roughly 20 degree phase boost using the improved model. So, that means the accurate model is not exactly same as the first order model. So, that means whenever the modulator is considered, that means if you consider a ramp compensation, then the first order model is not accurate. Okay. So, we have checked. Now, we can also check the link to output impedance. So, we can also check if we want to check the output impedance of these two, let us check it. So, we can check the output impedance, closed loop output impedance, can uncomment, and we can also check the closed loop output impedance of this. Okay. So, when we output impedance and here also, okay, and now we want to plot along with this, we want to plot on top of this in figure 3. We want to plot board A, the output, this is my okay. So, these are my closed loop output impedance because of the outer loop close, and at high frequency they are actually. So, we have to restrict our switching frequency to, should go to hertz, then limit to 5E5. Yeah, so they are matching quite accurately. This is open loop output impedance, and that in current mode control this is pretty high at low frequency because it is a load resistance dependent, and load resistance is 1 ohm, so it is 0 dB. And but using closed loop you can reduce the output impedance significantly. Okay, all right. So like this. Now current mode control also have a natural sampling effect, and this was reported in this paper 1981, that if you take cycle by cycle and if you take the part-up current, you will find this part-up current will change at every switching transition. So that means any perturbation will remain fixed throughout till this next switching event comes, and that inherently introduce some kind of a sample and hold effect if you take the current dynamics, and this effect can be introduced if you take a discrete time model. So discrete time model can be used to capture this sampling effect, and this natural sampling effect, after discretization and using continuous time model, Ridley model actually captured that, and that introduces another loop. So this earlier we have neglected K2, which was very small. The K2 was very small, it was small, they have ignored, otherwise this loop will come, and we consider current loop, right, and this HAS is coming due to the sampling effect. That is the term which was derived from the discrete time model, then from conversion from discrete time to continuous time, from that the natural sampling effect was captured. Okay. So the overall control to output transfer function by including this sampling effect can be derived, and in many commercial products actually use this technique, so that the sampling effect can also be included, because that is very important, particularly when you go somewhat close to the higher duty ratio, then the subharmonic, then other problem will come into picture. And we have seen also the high current loop gain, there is a significant mismatch. In fact, the modulator magnitude is also different in the different method, and that was one of the one of the major research topic in 1980s 90s time, when the researcher was trying to find out the accurate modulator gain for the current loop gain, at the same time and to incorporate this sampling effect. So with this in this course we have in this particular session we have recap, like a first order model, approximation model was discussed, more accurate modeling techniques were discussed, MATLAB case studies for model matching was also discussed. So with this I want to finish it here. Thank you very much.